Hey, Sec 230 students. This is the week 2 Muddy Points review. So questions from basically chapters 5, 6, and 7. Let's just jump right in here. The first one here is I would like a z-score table to be given to us from you specifically. Maybe I missed this somewhere. Yeah, it is available to you in a couple places. So if we go into our class, if we go to week 2, this is it. So if you click on the statistical tables, it is the entire packet that you're going to need for this class. So my suggestion is you print this off. So it's 12 pages. We're going to be using the first 4 pages here. That's the unit normal table or the z-score table. And then once we get past that, you'll see that it moves into the t-distribution, which will be chapter 9, 10, and 11. We'll be using that. We'll skip the Fmax. Then we'll be doing the Fmax or F-distribution when we're doing ANOVAs. And we'll be doing correlation after that, which is this one, the Pearson correlation, and then the last one here is the chi-square. So those are all ones we're going to be using. So this is yours printed out. You're going to use it from every chapter from this point on. Okay, so that is, again, it is available in right at the beginning of week 2 directly in the module, but also you'll find these tables every time, basically this chapter or this week on in the resources, you'll see the statistical tables. Okay, so that's where you're going to find that. In terms of the next question, this was kind of funny, cute. I would say I could do better at probability. I've noticed that every topic is 50-50 for me. There's a 50% of me that gets it, the other 50% of me decides to practice it and gets it wrong. But it did take me a few tries with the probability portion of my math class, so I feel it's going to be the same with this class. First off, I thought that was maybe not on purpose, but I love that you're using probability to explain your difficulty with probability. Because essentially what you're trying to do with probability is predict the future. And so the issue here is can you, will you be able to get the question right? Well, you're saying it's about a 50-50 shot. So probability really is just trying to predict an unknown future. So we don't know how it's going to go, and it's just odds. And that's key thing to understand with probability is that, if there's a 90% chance of something happening, that means it's likely to happen, but it doesn't mean it will happen. 10% of the time, it won't happen. And what you'll see is that a lot of our research conclusions, because they're using statistics, because we're sampling from a population and we're only doing our study on a sample of that population, we don't know the answer. We're just guessing. And so we're just adding what's the probability we're right. So this is often a place where people are, it might be a revelation regarding how scientific research often works, especially if it's using statistics, is a study that says A causes B. This treatment reduces depression. Doesn't mean it does. It means it probably does or probably would in the future. It doesn't mean it will. And that's probably a little, disconcerting because, a lot of medications you're taking are based on these research studies that are basically making probabilistic statements. So I will say that your concern or this person's concern is normal. Most people struggle with probability. And again, I like your description of 50% of the time you feel like you get it, 50% of the time you don't. It's a fuzzy concept. Our brains are not built to live in this place of uncertainty. Probability is a place of uncertainty. We don't know for certain what's going to happen, but we can make better decisions based on what's likely to happen or probably going to happen. And so that's essentially how we're going to be using it. I will say that as far as calculating probability in this class, basically chapter 5 is it. But we use probability from this point on in the class because all inferential statistics is simply based on making probabilistic guesses. Okay, so, but I will say, and this is a common thing I tell my students in this class, is there's going to be a point in class for most students where you can do everything I'm asking you to do, but you're not really sure why you're doing it. And you're not really sure or comfortable with the interpretation. And that's because of probability. And so that's a normal place to be in this class. Most students don't quite get their heads fully around it by the end of the semester. I think I've come to believe that it probably takes a second or a third statistics class before, for many people, that stuff starts to sink in. So, because you're not planning to be necessarily researchers or statisticians, it's not going to matter too much. Okay, next question is sampling distributions. This seems a little bit questionable for me. I don't really get the concept at all. So, what I would say for sampling distributions is what sampling distributions really are about is like, okay, think back to chapter 2. You learned frequency distributions. So we did it for a group of people, and we can get a distribution of where all the individuals in that group scored. We could do it with a frequency table. We could do it with a histogram or other frequency graphs like bar charts and line graphs and dot graphs and so on. So all we're doing with a sampling distribution is, instead of taking an individual score, a bunch of individuals, and graphing their scores, we're taking a measure of a sample and then doing that over and over again, taking a bunch of different samples and calculating some statistic. What we use and what we're predominantly using for us is a mean. So we take a sample, let's say there's a population, okay? And let's say it's IQ scores. So intelligence test scores, mean of 100, standard deviation of 15 for an individual. Right? So let's say I sample 20 people, give them an IQ test. I can take those 20 people and calculate their mean. Okay, so that's a statistics about that sample. Let me take another 20 people, give them the IQ test, calculate their mean. Take another 20 people, give them the IQ test, calculate their mean. Do that thousands, hundreds of thousands, millions of times, theoretically, right? What I would have is hundreds of thousands or millions of sample means. So what I can do is create a distribution of those sample means. I graph it. And that graph is technically a sampling distribution. Similarly, I could take, again, 20 people, give them an IQ test. Instead of calculating their mean, I could calculate their standard deviation. Take another 20, calculate their standard deviation. Take another 20, calculate their standard deviation. Do that hundreds of thousands, millions of times. I would now have a million standard deviations. I could graph that. That would also be a sampling distribution. So sampling distribution just simply means what we're graphing is a statistic coming from samples. And we're just taking repetitive samples over and over again. All right, so for us, the important one is the means. Because ultimately, in a research study, we're going to give people a treatment, and we want to see, do they end up scoring higher or lower than untreated people do on average? So we're going to take their sample mean and we're going to compare it to this mean of untreated people, and we're going to see, are they higher or lower than that? That's why we're wanting this distribution of potential sample means. Okay, so that's the main thing in terms of, understanding what we're doing with sampling distributions. It ultimately leads us to the central limit theorem. So in chapter 5 and 6, we're just dealing with individuals. So we're not taking samples of multiple people and calculating things based on them. We're just sampling individuals. And in that case, when we're using individual scores, they're not technically called sampling distributions. So I could get a distribution of a bunch of individual scores. That's just a distribution. Okay. So where sampling distributions comes in is once we start working with samples of people. Instead of just taking one person and looking at them and trying to measure them and understand them, we're going to take a group of people and calculate their sample mean, and we want to understand how normal or weird is that sample mean. That's why we care about sampling distributions, and then that's why we care about the central limit theorem. Okay, so that's our next topic here, and as you can see, this is the main place where people have questions. So really, I'm going to kind of cover this in a couple different ways. So in terms of the central limit theorem, essentially, I'm not going to worry about whether you can define it. I'm not going to test you on that directly. Really, in this class, all you need to know from the central limit theorem is how to apply it. So you just need to do a couple steps that the central limits theorem tells you that you can do. Essentially, it predicts how things play out if we were to do stuff theoretically. Um, so as long as you can do that part, that's the part you really just need to be able to follow. So like you're just going to follow these steps. So I'm going to cover that at the end here. But before we get to that is let's just talk a little bit about what does the central limit theorem cover. Essentially, the central limit theorem says that when you take um, it's this idea of those taking those multiple samples from a population. Um, what the central limit theorem ultimately allows us to do, and it's because we're working with z-scores, and we know z-scores, if they form a normal distribution, we can use our unit normal table, and then we can know all sorts of probabilities and proportions, and it gets really helpful to be able to do that. So how do we know that a distribution of sample means? So again, we're talking about sampling distributions. What if I took samples of 20 people, gave them the IQ test over and over again, samples of 20 over and over again. Every 20 people I take, I give them the IQ test, I calculate their sample mean. I've got a sample of 20 is their sample mean, another sample of 20, their sample mean, another sample of 20, their sample mean, etc. And I just keep doing that. Instead of having to do that, central limit theorem tells me how it will all play out. That's really all it is. That's why we care about it. And what it has three components, and those three components allow us to then be able to calculate z-scores. And that z-score will tell us how unusual a sample mean is. Because think about it, z-score just simply measures whether you're above or below the mean. If it's a positive z-score, you're above the mean. If it's a negative z-score, you're below the mean. Okay, whether it's for individuals or sample means. The z-score number tells you how far above or below, but it's on the scale of a standard deviation. So when we do it for chapters 5 and 6, it's on the scale of a standard deviation for an individual. So let's say we have exam 1 and you all have a score on exam 1. Let's say theoretically, the exam 1 scores in this class were 85, standard deviation of 5, right? So if you had a 90 minus 85 means your deviation is plus 5. You're 5 points above the mean. If we divide by the average deviation, which is our standard deviation, and I said it was 5, 5 divided by 5 gives us 1. So we have a positive 1. That's your z-score. You are 1, because the z-score is a 1, above, because it's positive, the mean. And it's 1 what? You're 1 standard deviation above the mean. So a z of positive 1 tells us you're 1 standard deviation above the mean. Now, that is a reasonably, it's above average. It's not super weird. So let me just show you quickly one of the things that can be sometimes helpful. Oops. There we go. Is when we have a distribution that is normally distributed. Okay, so you want to, get used to kind of drawing things like this. This is roughly where standard deviation of positive 1, standard deviation, negative 1. So if we're talking, these are actually z-scores. A 0 z-score means you're right at the mean. If you're positive 1, you're 1 standard deviation above. If you're negative 1, you're 1 standard deviation below. And then we can go up here is positive 2, down here is negative 2. But what you can see is that in the middle here, that's a lot of individual scores. And so anyone who's scoring in there is pretty typical for the group. So think of this as a group of scores on the exam 1. And if it was normally distributed, we'd say, okay, yeah, but a lot of people, if they're essentially, remember our mean was 85, standard deviation was 5, so that means this is a 90, this is a 95, that's an 80, that's a 75. So a lot of people are scoring between 80 and 90. So that's kind of, typical. But, again, a z-score of 1, if that person had the 90, they're definitely above average, but they're not unusual. It's when we get out here where we start to see in these extremes out here, this is where we're getting extremely high scores, extremely low scores. And remember, the height of this graph is depicting how many people. So ultimately, we have very few people who are scoring that high or that low. And they're very different from the mean. And so that's where we start thinking somebody is unusual. So ultimately, when we're dealing with a z-score, the number itself is telling us above or below, positive is above, negative is below, and then the number itself is telling us how many z-scores, or sorry, how many standard deviations you are above or below. And if it's a higher number, you're more unusual, right? So what we essentially want to be able to do then is, instead of just working with individuals, because again, our goal is to think about research. And we're talking about research where we can't measure the entire population. And what we need to do is take samples. And so we could do research studies where we just sample one person. So again, these might be, test scores, but maybe right before the test, I offered people a smart pill, and I want to see, did that smart pill help them do better on the test? Well, let's say that person ended up with an X of a score on the test of 92, right? So then we're going to locate them, and they'll end up being 92 minus 85 over 5. So that's our z-score, right? Is X minus the mean over the standard deviation. Actually, we'll do mu. All right, so X minus the mean over the standard deviation, and we end up with a 1.4. So they're above average by 1.4 standard deviations. So they're 1.4 standard deviations above the mean. So they're about here. Okay, not bad. But is that enough of a difference? Are they doing so much better that it's clear that it has to be due to the smart pill and not due to possible sample error? That I just happened to sample somebody who was going to do that well. And that's not that unusual a score. It is definitely above average, but it's not that unusual. If it was out here, that's where I would start thinking, it might be that smart pill actually works. So that's what we need to be able to do. Now, we just did it with an individual. That is not a great research design. So individuals can be just different due to sampling error more likely. So what we might want to instead do is do a sample of 20 people or 40 people or 100 people. Give each of them the smart pill and then see, do they score higher? All right, so in that case, we can't compare them to individual scores because individuals have a mean of 85, standard deviation of 5. We need to compare them to a distribution of sample means, and that's ultimately what we're trying to do. So here's essentially the ultimate goal of what we're trying to get at here. So real world examples of central limit theorem, still a little confusing. Having a challenge visualizing what it means. The sample mean will be approximately normal in central limit theorem. How is this possible? And I'm just muddy on the central limit theorem. It makes sense to me, but I haven't fully understood it. Just clarifying a bit more. Maybe doing a couple more practice problems can help a lot. Absolutely, always practice problems. But here's how you're going to need to be able to use the central limit theorem. And this is partly getting into some of these questions down here. So we'll come back to those once I show you what I'm doing here. All right, so the idea is, here's what you need to be able to do. All right, so let's say, again, we knew, in this case, let's just take a topic of IQ scores. All right, so we might know IQ scores, we would be told have a mean of 100 and a standard deviation, of 15. We're going to take a sample of 25 people. All right. And we're going to give them some kind of smart pill. So we're going to give them an IQ test and see if this smart pill makes people smart. All right. So instead of just taking one person, giving them a smart pill and seeing how they score, because that's what I could do. I could compare that to this. All right. So first off, here's what I would do. So this is individuals. This is the distribution of individuals. So I'm given that information in the question. All right, so mean of 100. So I can label this middle line here, mu 100. Standard deviation 15, I can label that on here. Here's how I usually do it. I do a line, a horizontal line, and then I'll just indicate it here. Okay, so again, visualizing it, you can say, okay, there's about 115, and this is 85, and then up there would be about a 130, and down there would be a 70. And so we can kind of get a sense of where people tend to score on an IQ test. Most people are going to be between 85 and 115. Okay. Now, if I didn't do a sample of 25 and I just gave a smart pill to one person, I would look at their score and then I could compare it to this to see how unusual it was. So let's say I took one person, gave them the smart pill, and they ended up scoring a 135. That puts them way up here. It's very weird. It's a high score. Ultimately, would be a z-score of 132 minus 130, or sorry, 132 minus 100 divided by 15. So it would be 32 divided by 15 would be 2 point something. All right, so it is pretty unusual. And we can see that there's just not that many people up here. Remember, if we shade things, we can shade regions, and how much of the entire shape is shaded gives us the proportion of people who are in there. And very few people are up in this little tiny spot. Okay, so it would be an unusual score, and we might be, again, wanting to conclude that that smart pill possibly works. There's two explanations. The smart pill made them do better on the test up here, or they were already up there. And what we're trying to figure out is what's the odds that they were already up there. That's ultimately what we're going to be doing in inferential statistics. And as long as that's really low, then we're going to choose the other option, which is that the smart pill worked. But doing that with one person, you can see how it doesn't really make a lot of sense because it's so likely to get somebody who might happen to score that high. And so as a result, what we do is we're going to take 25 people, give them a smart pill. All right, so if it turns out that that group of 25 people has a sample mean of let's see, 109. The question is that noticeably different? Is that evidence that there's probably a treatment effect, that this smart pill is making them smart? Now, what a lot of people will then make the mistake of is they'll compare that 109 to this distribution. And they'll locate 109, it's about here, and they'll say, yeah, that's a pretty typical score. The problem is that's a sample mean. Technically, as we indicated here, this is a distribution of individuals, so we can label this with an X, and that's an M. This is a distribution of individuals. What we need is a sampling distribution. We need a distribution of sample means. And that's what we can compare this to see if this is unusual. That's what the central limit theorem tells us. So central limit theorem tells us to do three things. First off, it says it's going to describe three things. It's going to describe the shape. It's going to describe the middle. And it's going to describe the spread. That's essentially what it predicts. So think of the central limit theorem as a prediction. It says, what if we took sample sizes of 25 from this population? So this is millions and millions of people, all adults in the world. This is how they tend to score on IQ tests. Mean of 100, standard deviation 15. I'm going to just grab randomly 25 people from this distribution. I'm going to give them the IQ test, and I'm going to just calculate their sample mean. And I'm going to do that, grabbing 25 people over and over and over again. For each of the 25 people, I calculate their sample mean. Central limit theorem simply says this is what the distribution of sample means would look like. So it predicts the sampling distribution, and it predicts specifically the distribution of sample means. First off, it predicts the shape. The shape will be normally distributed. Okay, so I can draw a normal distribution. Why does it predict that? There's two rules that essentially predict whether this is going to be normally distributed. The first is if you're sampling from a normal distribution. This is a normal distribution. So it often will say that in the question that the distribution of IQ scores is normally distributed. If it doesn't say that, just assume that. Everything in this class will make that assumption. So as long as you are sampling from a normally distributed population, your distribution of sample means will be normally distributed. Okay, now I can label this with an M because this is a distribution of sample means, not individual scores. All right. So the other rule that makes this normally distributed is as long as your N is at least 30. So ours isn't 30, so we wouldn't be able to assume that unless it was normally distributed, and it is. So we're good. Every question you're going to have in this class makes this assumption, so you don't have to worry about the whole sample size thing. Now, the sample size thing did come up in a bunch of the interteaching things. Just know that that 30 is not a hard and fast rule. It partly depends on how screwed up the normal distribution, or the population distribution is. If it's super, super skewed, then you might need a higher than 30. 30 was just kind of a rough area, but it's not that 30 also does not mean that any research study needs to have at least 30. No, it's in order for the distribution of sample means to be normally distributed for a z-score, which is a very specific type of research study. 30 tends to create a distribution of sample means that's as close to normal as you probably need it to be in order for your probabilities to work out. Other than that, like researchers have to spend lots of time thinking about how big their sample sizes should be. And that 30 is not just a easy rule. So just wanted to kind of clarify. Okay, so, but we never have to worry about it. So what we want to do is create this distribution down here. You're welcome to draw this distribution. I always like to. It's a good reminder. What's the mean? What's the standard deviation? You don't have to do all this other stuff. I often label it X, so as a reminder. But then what I want to create is the distribution of sample means. Oops. That should be N. Okay, so this is the distribution of sample means. Now, I've already done the first thing. Central limit theorem tells me the shape, normal distribution. Central limit theorem tells me the middle. So I can draw there, and it tells me what the mean is. The mean of all of these sample means. It's equal to the population mean of individuals. So I just do mean equals 100. Okay, so it's almost always first two steps are super easy. Just draw a bell shape because we're always going to be sampling from a normal distribution. Label the mean in the middle with whatever the mean is given to you in the question. So now we know that. So now we can see that a 109 is above the mean. We kind of already knew that, but that's where we're at. The question though is how far from 100 is this mean? And that's where the third part of the central limit theorem comes in, the spread. Central limit theorem predicts the standard deviation of all of these sample means. All right, so here's what I always do. I just do this, and I do standard deviation sigma sub m. It's technically, whenever you do this, that's the symbol for what you're calculating, and that's the Greek letter sigma, so that means this is a standard deviation. And then in the subscript is what it's a standard deviation of. So it's a standard deviation of all of these sample means. Again, theoretically, we take a bunch of samples of 25 from this population over millions of times, creates this. How spread out are they? That's what that's calculating. Technically, that's also a sigma. That's a standard deviation. Technically, that is a standard deviation sub x. We just don't put the x in by standard. So we just leave it out, but that's essentially what it is. So that would be what would be in the subscript if we use that. Okay, so what we're calculating here, though, is the standard deviation of the sample means, and that's what the central limit theorem tells us for the spread. It's going to be equal to the standard deviation of the population divided by the square root of the sample size. Okay, that's what the central limit theorem tells us. So in our case, we can just go up here. Standard deviation of the population is 15. Sample size is 25. So take square root 25. So we got 15 over 5, which is 3. Okay, so what it tells us is that this is 3. So again, you can start to think this is like a 103 here. Here's a 106. And where would 109 be? Because that's what we want to look at. It's way out here. That is an extremely high sample mean. It is 3. Ultimately, we would then calculate the z-score for it. So our z-score for sample means is m minus mu over standard error, or sigma sub m, standard deviation sample means. So we have 109 minus 100. Again, the 100 is just that, also given to me in the question. And then the standard error is what I just calculated at 3. So you see it's 9 over 3, positive, which is a positive 3.0. It is ultimately 3 standard deviations above the mean. That is a very unusually high sample mean. Again, and if we gave those people a smart pill before giving them this IQ test and they ended up scoring that high, at this point we have 2 possibilities. We happen to sample 25 people who happen to be super smart and have an average IQ of 109, or the smart pill is making them smart. Those are our 2 options. What we just can figure out from looking at the z-score is that is an unusually high happening by chance, because these are all the sample means that just happen by chance. These are untreated people. And so that 109 can happen. Yes, we can sample 25 people and have them have a average IQ of 109, but it's very low probability. So we have these 2 options, and one of them is really low probability as it's going to turn out. And this is how we do the shading and all that. We can shade, what's the probability of getting a Z of 3 or higher. And that's the other thing that we can do here, is we can convert these to z-scores. And there's a 3, right? And so we can say, what's the probability of getting a Z of 3 or higher? And we can then shade that. And so we'd have this very barely shaded little thing here. And if you look up in your unit normal table, you'll find that the tail for a Z of 3 is very, very low probability. So again, how likely is it to have a group of people, 25 people, end up having a sample mean of 109? It is a very low probability. And we have these 2 options, one of which is very low probability. We're going to choose the other one. So we're going to say, yeah, I think the smart pill made people smart. Are we right? Probably. We don't know. It's still possible, low probability, but it can happen, that this was just happened by sampling error. And again, because also we have to think about it, no one's invented a smart pill yet, so unlikely that it exists. So, but this is how we would end up publishing this study and saying this smart pill seems to work. We think it probably works. And then what you need to do is do other studies. And so we need to see 10 or 20 other studies on the smart pill before we can really ultimately get pretty confident. But at this point, this would be evidence that would support the notion that we might have an effect here. Okay, so that is the some of the essentially the usage of the central limit theorem.